Yay!
Yay! Just like we found the electric field for continuous charge distributions, we can do the same thing with the potential. And it turns out that doing it for the potential is usually easier. And there's a little trick so that if you calculate the potential for a continuous charge distribution, you can get the electric field maybe a little bit easier than trying to solve for the electric field directly. Here's kind of a simple case. It turns out that the electric field of a ring wasn't that hard anyway, but I'll just show you, this is sort of a typical problem. I'll just show you the technique because it turns out that this is easier for more complicated systems. Okay, anyway, suppose I have a ring. Let's go back to the ring. So it's a ring of charge plus Q, and it's a ring of radius R sitting in the XY plane. And I want to know at some point, let's say up here on the z-axis, I want to know what the potential is. Okay, so it's almost the same thing. The potential is just going to be K. I mean, the potential from a point charge is KQ over R. But we're dividing this thing up into lots of little tiny DQs, right? Little tiny segments. And so we have to add up all the little potentials made by these DQs. So it's just going to be adding up all the little K DQ over R. And just like before, I'm going to try to go from 0 to 2 pi because I want to go all the way around the ring. Just like before, I'm going to have to do I'm going to change variables to theta. So dq over q, a little bit of charge compared to the whole charge is like a little bit of angle compared to the whole angle, 2 pi. So I get this. I'm going to have, let's see, substituting in for dq, what's that going to give me? dkq over 2 pi. And then I'm going to have, and then my r is going to come out, right? Because it's here's my distance r from dq to the point I'm interested in, but that doesn't change as I sweep around the circle. So r can come outside the integral. So this is actually going to be really easy. 0 to 2 pi times d theta. Okay, well, that's just going to be 2 pi. That cancels that 2 pi. So look, this actually is really simple. KQ over little r. But like before, let's write it in terms of things that we know about the ring. Usually that's going to be radius and then distance away from the center z. So what is our little r? That's just going to be r squared plus, usually for some reason we write it the other way around. Usually it's like z squared plus r squared to the 1/2, right? It's just, in fact, I don't need to even be that fancy. Why don't we let's just say it looks like that. There we go. So that is the potential, some distance z away from the center of the ring. Okay, yeah, that was actually really easy. But just to prove the method, let's find, can we find the electric field? Let's find the electric field. How do we do it? Well, we can use this. The electric field, the z component of the electric. Okay, let's write it in general. In general, what you've probably seen is that the electric field is negative gradient of the potential V. Okay, what the heck is that? So what is the gradient? That is negative, and the gradient is partial V with respect to x in the I direction. In fact, in the vector notation, I like to use, let's write it nicely like this. It's minus, and then it would be partial V with respect to x. That's in the I slot, the x slot. Partial V with respect to y, and partial V with respect to z. There we go. So that's the gradient. So that means that if I want, and we already know the electric field only has the z component, right? So Ez is just minus partial v with respect to z. So if I know what v is, all I have to do is take the partial derivative of it with respect to z, and that should give me the electric field, the z component of the electric field, but that's the only component of that electric field. Okay, let's find out what it is. So Ez is just going to be minus partial with respect to z. Let's see. What is v? It's just going to be kq times z squared plus r squared to the minus 1/2. That's the thing I want to take the derivative of. Okay, I can do that, no problem. kq, that just comes right out front. I've got a thing to the minus 1/2. So if I take the derivative of it, I'm going to bring the minus 1/2 down. So the negative sign goes away. So this is just going to be kq, there's my half. And then I got the thing, z squared plus r squared. So it's the thing to the minus 3/2. And then it's chain rule. I got to multiply times the derivative of the thing. So that's just going to give me a 2z. Oh, that's nice because the 2's cancel. So what is Ez? Ez is just going to be kqz divided by z squared plus r squared to the 3/2. Well, look at that. If you look back, that is what we got for the electric field. Cool. A lot of times, now in this case, maybe not so much, because that really was sort of an easy electric field to find. But sometimes, I'm just putting this in the back of your head, sometimes you'll get to problems where you want to find the electric field from some charge distribution. And it turns out that because the electric field is a vector, that's a real pain to figure out. It's not easy. But it is easy if it's just a number. So a lot of times finding the potential is easier because there's no vector involved. It's just this up here. So a lot of times that's easy. And then to get the electric field, you just take its derivative. And usually that's not so bad, right? A derivative is just a mechanical process. You can take the derivative of any function if you're patient enough. So that is sort of maybe a shortcut. So find the potential. If you want to find the electric field, sometimes you want to find the potential first, and then just take the derivative or the gradient of the potential, and that'll give you the electric field. So that's sort of a neat relationship between the two.